Hi, everyone. Welcome to Talk Math with your friends. It's my pleasure today to introduce Lauren Siegel of the Math Happens organization, and she's going to tell us about math outside the classroom. Please join me in welcoming Lauren.
Thank you so much. I am really excited to be here. I started looking at your other YouTubes of previous presentations, and it's a really great group with some high math topics. And I hope that you enjoy today's presentation. I'm excited to share what we've been doing for the past 5 years. My undergrad math was at University of Chicago. I took some time working in parenting and ended up at University of Texas UTeach program to get a teaching credential. Worked at a small private school for gifted kids, really trying to implement the UTeach philosophy. I was there right at the start when it was just at Texas, and now they're all over the country. When I had been doing that for 5 or 6 years, I needed a break and actually learned how to make things on a laser cutter. And also some resources that we had put aside as a family back in 1999 started to accumulate to something that we could maybe use as a nonprofit. And we wanted to increase the visibility of math in the community. We tried making some donations, and what we found out, I'm going to go ahead and share my screen, is that that's not the screen we want to see. That's the first thing we can find out. What we found out is that there wasn't really anybody to just give money to and have math suddenly appear in their museum or wildflower center or other place. And so did a rethink and decided that we would try to just do that. Joined the museum partnership and returned to UT to recruit some interns. What we are trying to do is get math outside the classroom. More detail on that is to increase opportunities to learn out of a school. You know, people don't have to stop learning when they're no longer in a K-16 framework. To practice transferring applications from one context to another, diffuse math anxiety, let the public meet people who like math, celebrate mathematical accomplishments, and connect to culture, history, and community. I can say those were our goals 5 years ago. We just wanted to get out and talk about math, but had this been our goal list, I can say we have achieved it, and I kind of wrote it looking back on some of the things that we've done so far. What's the problem? Why do we need to talk about math outside of school? 40% of fourth graders are proficient at math, 30% of adults lack basic math skills. So there's 60% that are not proficient at math in fourth grade. And there's a lot of parents out there that aren't very comfortable with math. This was something from last fall, the old world. And the then director of National Council of Teachers of Mathematics was talking about ways that you can help your child enjoy math. And none of his suggestions involved going to a museum or going out to a zoo or cultural center or even the library to do the math activities that are there, because they're not there. And it just seemed like this huge void that maybe we could start to think about, what can we do? What are museums talking about right now? And I just went today and pulled this off the American Alliance of Museums. We went to our museum partnership, which doesn't exist the same way in every city, but they were a great way for us to get access and exposure to all of the different kinds of places. The Nature and Science Center, which is run by the Parks District, is in there. The Texas State History Museum is in there. We have historic house museums. We have a Ransom Center, which is a rare books archive is in the partnership. So we gain access to all different kinds. This is a national group. And a year ago, museums were talking about being centers of wellness. They kind of strive for relevance in a very distractible world. And they also take their education programs very seriously. Field trips are very important to them. And just trying to create community cohesion wherever they are. Today, they're talking about being trusted. I don't know if you can see it, but the math problem on the chalkboard is 1 + 1, which could hope for more, but at least it's there. And there's a little squiggle graph and some things like that. Museums have been trying to offer STEM programming. And if you're not a parent and kind of exposed to those programs, there's almost never any mathematics in there. They will launch something and say parabola, and that's about it. So again, opportunities to do more. People love museums, and that is something that attracted me to this idea of working in a museum. People have this open attitude. I'm just going to go and learn whatever there is to learn at this place. And I'm going to be with my friends and my family, and I'm going to have lunch and all those great things that we love to do before we got trapped in our houses. Our interns, because they're pre-service teachers in the main, they like math and science. teaches math and science students to be teachers. And so they're good at explaining math and science. They would go learn how to use the laser cutter and do research with us. And they have been amazing, great ambassadors. We have worked with all different kinds of organizations. We even went to MoMath and gave an evening presentation there. Lots and lots of really good partnerships. So let's just check for a few things. We make things like these hinged mirrors. This is, you can't see the map, it's a Mercator map, but this is a math student. We had to recruit extra people because we actually had all the tables at this HEB Free Sunday. And I just want to emphasize that for a student who is studying mathematics, to have an opportunity to just talk about math and tell what's interesting about it is really great. There's kind of a high that you get from talking with multiple people and explaining something cool and interesting about math. This is outdoors at the Nature and Science Center. I have struggled to explain this problem, calculate the size of the planet. In this case, you look at the kids' shadows. You can see the shadows of their bodies, but there's no shadow from the sticks. And so what we're seeing here is that light comes in as a ray, and they all come in parallel to each other. So they have manipulated their sticks to show that. We have lots of cannonballs in Texas, cannonballs everywhere. And so we actually built these frames, sized them to work with ball pit balls. And little kids love this, and math professors love this. So hit two groups right there. This is an outdoor sculpture we commissioned. And the 3x3 is a Penrose stair. And then the guys made X's and O's so we could play jumbo tic-tac-toe. The 4x4 is actually subdivided into an 8x8. And we've got we actually made chess pieces to fit on there and checkers. And then the 5x5, you can, it's etched out for that proof without words. The sum of the odd numbers, 1 + 3 + 5, is the square numbers. And we serve cupcakes off of that on museum day. Super fun. We make fractals and make fractal art. This little guy had to make all the pull string polygons. And just the happiness that a kid who loves math shows when they find something out and about is great. I'll go straight from there to the cemetery. Yes, of course. Well, it's Halloween. And early on, we had this question, can we really teach math anywhere? And what would we teach? And this is, I think this is actually fall 2015. And cemetery was having an event. They need to raise money because their tombstones are tilting and falling over. And so I said, okay, we're going to come out and do something. Well, fortunately, I was reading the cemetery newsletter on my research, and they were raising money because their tombstones are falling over. So we made this custom-made square with a degree gauge, and it fits for what's going on, why they're having their fundraiser. You can extend the thinking to how would you decide which tombstones to fix first, the ones that are falling fastest or the ones that are falling the most. And you would, take those measurements with a device like this. We actually had a professor from Austin Community College happen to that event, and he contacted me later and said he wanted some more of these squares so that he could use them with his class. And he was going to take the cemetery back to his class as a context for talking about these angle measures. So that was kind of interesting too. And we enjoyed that event. Another challenge, space cowboys. This was a popular culture exhibit. It had Star Wars and cowboys and cartoons and comic books. But the first thing was an 1874 original edition of From the Earth to the Moon. I have not read that book. On the tour, people said it's really interesting and it's got a lot of satire in it. I thought, okay, we're going to go to their opening event with the table and activities. What are we going to find to connect? How are we going to connect to these cartoons and Star Wars and stuff? And what we found is this book is about a gun club. Civil War's ended, and all these guys that love guns don't have anything to do. In order to get into the gun club, you have to design a gun. And so there's this really cool math language. I actually didn't show this to anybody. The estimation in which these gentlemen were held, rank in the club, according to one of the most scientific exponents of the gun club, was proportional to the masses of their guns and in direct ratio of the square of the distances attained by their projectiles. Okay, so they gotta win this, right? How are you gonna win the gun club? They were going to fire a rocket. Uh-oh, what's going on? To the moon. Okay, so they get these guys together, and there's another picture with two guys and a dog, and they're in their rocket ship. Now they're worried. They've taken off. They're not sure they're going to clear Earth's gravity or fall back down, and they're doing all these calculations. And so we have this really awesome image. They're, talking about the calculations, and do you understand it? And he says, yeah, I understand it, although your X's and zeros and algebraic formulae are rattling in my head like nails in a bag. So we actually have nails in a bag for people just really, experience that. And since 1874, we've had this problem, right? People just get rattled up with math, and it's a great way to start that conversation. I show a slide that includes this when I talk to museums, and we do a little pop-up quiz. How do you feel about math? Okay, nails in a bag is usually one of the choices, so they can kind of let us know how they're feeling. And it was also just a really fun thing because this book's under glass, can't touch it. Let's get it out from under glass and look inside it and hopefully find a way to talk about math. One more observation kind of in the nails in the bag is classroom mode versus field trip mode. And this actually was a field trip, and we had a classroom portion. And I'm going to give you a moment to look at the body language. I think we could sit and discuss for a while, or we could just move on. This, I didn't realize when I was taking these pictures, and I looked back later and we had a discussion and we decided we are not doing any more paper pencil. We have to find a way to make a model or something you can do or touch or experience. We can't communicate this way anymore. And with that said, I would like for you to get a piece of paper and a pencil. It's a new world. And, I'm going to have a problem because I have no idea what time it is. No.
It's 10 to the hour, so it's 10:04 p.m.
2:48. Okay, we're going to go. White paper and a pencil. Okay, the first thing you are going to do, and this is the optional activity, draw a cartoon snow, like just circles, little fat circles that are falling, about 20 snowflake. They're not flakes. Don't make them flaky. They can just be circles. So fat dots. And towards the middle of your page. We're not going to really use the edges of the page. And, you know, about 20. If you're comfortable showing your snow, love to see it. Okay, now that's awesome. Okay, now we are going to imagine a segment between two snow flakes that are falling, and find the midpoint and kind of draw the perpendicular bisector. So between two snowballs, we're just gonna put a little line. And then do that for all your snowballs. Just a little perpendicular, where would the perpendicular bisector be for that? And then once you have your bisectors figured out, you guys are piloting this activity, by the way, because so I'm kind of excited to see how it goes. Okay, now we're just gonna gently extend those bisectors until they meet each other. And they should meet each other in some kind of a point. Sometimes 4 of them could be together. Sometimes it's just 2 because there's some kind of like little short thing. It's like 2, it's really gonna be 3 every time. And don't stress out about it too much. How's it going? I see a couple of faces. I get to see everybody. I guess I could unshare my screen to see everybody.
Excuse me.
Okay. Okay, so cool. Now that you've done that, you guys pretty much done?
Yeah.
I would ask you to consider whether you can make this drawing into a turtle. Don't do it necessarily, but maybe consider it. Like around the perimeter where you didn't have anybody to connect to, like sketch out a little circle space. Turtle shell. Don't worry about the, yeah, I see a turtle there. Oh, and there's a head. Cool. Nice. I like that one's up and moving.
So one of your instructions right back at the beginning
Yeah.
is to draw the perpendicular bisector. What it doesn't say is to omit the line joining the two dots.
Oh, I'm sorry. You're supposed to imagine the line joining the two dots.
I didn't. I made it. I made them.
What does it look like?
It's very, hang on.
A lot going on there.
Yeah, well, you've got it. Okay, for some value of head, there's your head with a jaw and a little eye.
Nice.
For some value of a tail and some value of legs.
Okay. So
it's just that particular thing.
Look at that turtle. Nice. Okay, we've got beautiful turtles. So now this is where, especially if you don't want to mess up your turtle, I would go with the pencil. Take one of the regions that's entire, like towards the middle, and put a square in it. And then put some like freckle dots in that region with the square, but not in the square. So, and then a few freckle dots over the border that are like falling out of that region, but not really going very far. Okay. What you have there was a turtle, but now it is the map of the cholera epidemic in 1850. That was the foundation of modern epidemiology. Your dots are now water wells, and the one in the region with all the speckles is the Broad Street well. These regions are called Voronoi regions. And if you stop and think about it, you've made bisectors between all the dots. And every position inside a region is closest to the dot that's inside that region, even though they're not regularly spaced. That is what a Voronoi region map is. And it was this kind of a map that helped them solve the cholera problem. The square or rectangle is important because it was the exception that proved the rule. The little speckles that you drew, those are people with cholera on your turtle. And the reason that there are no speckles in the square is because there was a brewery in that area close to that pump, and they gave free beer to everybody. Everybody just drank beer. And so nobody got cholera. So it was pretty interesting use of mapping. It was novel at the time, and it's considered the foundation of modern epidemiology. It's also a pattern that shows up in turtles, in giraffe, in snake skin, and a variety of other places. We put dots on a whiteboard, maybe if we're on a field trip at the nature center, and students work together to draw those midlines between the dots and connect them. And there's something about being up close to it and then stepping back and seeing that pattern that has a really cool impact. Or we put cones down and we try to walk between like they're, you know, dangerous landmines or snakes. Another way to think about it is if you are have a Starbucks or pizza restaurants and you want to know who are my customers, the Voronoi map will tell you who is in your area. I'm going to show you a couple of other things that we show with this. I'm going to try to link to this demonstration. I hope that it then shows to you. It's something that you find in Wikipedia. Can you guys see that?
Yep.
This is really what Voronoi means, that the region around your dot, but with respect to the fact that there are other dots. And if you don't have two very close together, you might not see what you see at the top right. Kind of mesmerizing. Okay, so let's see what happens now. That's not what I want to happen. Let's get back to this. And sorry, I might have to flip a whole bunch. Okay, so over here on the left, that orange arrow is actually mine. This is a map of the actual John Snow's map. You can get it from UCLA. You can print up a big one. You could laminate it and actually draw the Voronoi regions. The pumps are labeled on there. On the right-hand side, this is John Snow's actual sketch. And he went one step further and he said, where is the region within closest, what are the boundaries that are where the Broad Street well is the closest walking distance. And so he drew that. Oops. This is a map that you can find if you do Google. The blue dots are the wells. If you take that old original map, you should be able to generate something like this. That's that Broad Street well. So it's a great history connection. What do we do with kids though? We're trying to teach them something about this. We actually, somebody remarked, these are a lot like stained glass too. So we have kids choose giraffe, turtle, or cracked mud. And they take a vellum sheet and they actually trace out the pattern. What they're doing is extracting that pattern, right? They think they're making a stained glass craft. What they're doing is extracting the pattern. And what we find is that towards the end, after they've made their stained glass and colored it, that they can easily see that the turtle and the giraffe and the mud are all the same thing. So that's kind of what we do with them. There are lots of options and ways to show and talk about this. We have a field microscope and a dragonfly wing. So we look in the microscope and see that pattern in the dragonfly. We've got the giraffe and the mud. This is a puzzle still under development, right? These are orthocenters on triangles. You have to have the sides the same and you can puzzle them together. If you use all the regular pieces, you're going to get a regular hexagonal shape. So that's pretty cool too. These are a couple of the stained glass art. And then you can see on these two, these are modified Voronoi. One of them, if you're in a city with city blocks, what you consider how distance is going to be different if you can only travel along a grid. So you get a different kind of pattern. Are you guys ready to move on? Any questions or thoughts on Voronoi? It's a really fun one and a really great way to show some very disparate things all go together through this kind of mathematical pattern. Great. Texas State History Museum, our flagship. They have a ship that sailed in 1685. It was recovered in 1995. Took them until 2014 to, first they built that and then they moved the ship there. It's a really cool find. It had one skeleton on it. It had some kind of hand grenade, glass timers, some navigation tools, and a variety of things. So this is the flagship. They have a movie that kind of animates the story. Salle was on it. And it's a major destination. The museum itself is just beautiful too. So what did we do? We went there and we started researching what kind of tools of navigation would they have had. No sextant, but they would have a quadrant. And we started coming up with ideas of things that we could show and talk about. On the right, you see this shell. I think Henry Siegerman has it on the cover of his book. It's really fun to look through and shine a light through. But it also really helps us talk about Mercator maps. And at the time we first did this, the kids were very torqued up about the map and why is it distorted and is it Eurocentric or what's going on? And the answer is that Mercator maps are way better for navigating. You can put a ruler on it and draw a straight line, a rum line, follow your compass and get to where you're going. If you look right there, I hope you can see my cursor, that's Greenland. And then over here, this is what Greenland looks like on a Mercator map. So it's a big difference. If you look at the little windows at the top, well, the light needs to shine down a little bit more, but the windows eventually come to be all the same size. And just to be able to show that and have some understanding of what a projection does is really a high impact. People feel like they understand something that they didn't get before. I've got this screwdriver and nut driver there because we actually have students make this. It's a parallel ruler, something that wasn't invented until the Mercator map came out and you would want to find parallel lines. We look in the old books. You can get the old books and they're published in Google Books. This is an old Mercator map and lots of fun there. Let me check and see what time it is.
105.
105. Okay, so 405. So I have a question for you. I can talk in detail about a navigation thing, or I can give you a demonstration on pool testing. Raise your hand if you're okay with the pool testing COVID thing, or it's just pool testing. And somebody tell me who's winning, or navigation. Or I can talk real fast and try to do both.
Pool testing first, it looks like from the votes, I see.
Okay. So hot topic lately is pool testing. Trying to make an exhibit that will explain something about this because it's a big mystery. I am going to, oh, I see. What is going on there? There we go. Can I get, is it spotlighted?
Yeah, you might want to stop sharing your screen though.
Oh, okay, right. Forget the order. Thank you. I am very amenable to directions. So, okay, there you go. The way we have started this one actually is, and I'll show you the ads later, but there's newspaper article after newspaper article. The Israelis are using robots and supercomputers to pool test, and people in the US can do it, or we can test everybody, but nobody's doing it and it's too hard, or there's errors, or, you know, there's all this different information. There's also a really fascinating article out of Rwanda, which has very low resources. They are pool testing massively, and they're using things like cardboard templates. This really caught my eye because I'm all about making things and templates and stuff. But we're going to start out how we start out with the students, which is to say, and I'm going to just rig this. I've got some tap water here, and I'm going to put some of it in here and some of it in here. And I have some vinegar, and it's going to go into here. They're just clear liquids. I could maybe cheat by smelling them, but I'm not gonna. For reference, the way that we can kind of really animate for students limited resources is we can use pH strips, right? And just as a test, uh-oh, no one can see that.
Okay.
There we go. Can you see that?
Yep.
If I go with the vinegar, I'm gonna get orange at the top. If I go with tap water, I'm gonna get green at the top.
Sorry,
Everybody solid with that?
the paper that you have, you've litmus paper sitting on the white paper.
Yep.
Yeah, that's not actually visible. Can you bring
Yeah.
the white paper on top of the test tubes? Yeah.
Ah,
There we go.
there you go. This one was tap water.
Yep.
And this one was vinegar. Sorry, that's interesting because my view shows more. All right, so you guys start right here.
Yeah, that's yeah.
I can see it.
I could see it on mine too. Might be a weird Zoom thing.
You might
Okay.
have to change the view to show speaker view. That's how I got to be able to see it.
I am closing these up now. 2 water and 1 vinegar. Right? Everybody okay with that?
Yep.
Harm no foul. Now I'm shaking them up. I don't know which is which. And there's still 3 of them though. I'm gonna put them back in here and open them back up. And now my challenge is to find out what's in these 3 with only 2 tests. And a math problem person would say, well, use 2 tests on 2 of them, and then you'll know, right? The 3rd one is in. But that doesn't match reality. And there's something called fit to purpose that if you read about this, you will encounter as a phrase. You have to test all the samples. Somehow, some way, you got to test everybody. So what I'm going to do is a little magic trick, and your job, the student's job, is to make a graphic, draw a picture of what it is that I'm doing. So are you ready? Somewhere adjacent to your turtle that you could also turn into stained glass later if you want. Okay, here I go. I'm going into sample 1, and I'm going to put 1, 2, 3, 4, 5, 6 drops into this vial. And then I'm going to go into sample 2. And I'm going to put 1, 2, 3, 4, 5, 6 drops in there. And 1, 2, 3, 4, 5, 6 drops in there. And now I'm going into sample 3. Uh-oh. One, 2, 3, 4, 5, 6. All right, everybody feel good? They know what happened? Shake them up a little bit. And now, because we only have 2 tests, probably we're limited, we can everybody see that? Little strips,
Mhm.
Yep.
pretty much okay. All right, let's see what's in here. Okay, so we could stop and talk about what we know or don't know at this point. I'm going to keep going because I'm going to be out of time. I don't. All right, so which sample has the vinegar?
The one on the left.
The first one.
The first one. How would I know if the second one had the vinegar?
Both would be colored.
Both
Turn
would,
orange.
yeah. And how would I know if the one on the right had the vinegar?
The other one only would have been like the opposite result.
Yes, only this one and not this one. So this is, did anybody draw a picture of this that we can see? That would be a good one for your, oh, you're doing like a finger thing.
Yeah.
I'm trying to see. Anybody else got a picture they want to show? That looks great. That looks great. So we start out extracting this pattern, and then we can move into, well, what other kinds of pool testing are there? And because of time, I'm just going to show you some things that I built, because I think that students can design these kinds of things as well. You can see that with the plain rack, it's really hard to tell what to put where. And if you had hundreds of samples, you'd be in a lot of trouble. So this one is for 25 samples, and you would take each column, sample it into the bottom, and then you would test the bottom 5. Now you've used 5 tests. If one of those has a positive, you have to go back and test everything in here. What are the issues? I have some slides that show, now you have to do 2 rounds. If you're on a 6-hour PCR test, things are getting complicated. You're saving tests, but you're doing more rounds and you're looping back. What else could you do? Another thing that you could do is create a matrix. So columns, I don't know if you guys can all see that, would come down into here. And keep the group names the same. And rows would go into here. And I'm trusting your mathematical abilities to see this as almost an XY axis, where if this pool is positive and this pool is positive, then you know which one. So now you've used, in this case, 12 tests for 36 samples. So you can then start talking about, well, if there's 2 positives, then I have some that might be suspicious, but not known. There's pluses and minuses to this method. In those articles, and I have a link to all the articles, there are some really complicated contraptions. And so I got a little frustrated with all this talk of computers, and I decided to try to combine these things that I saw described into a contraption that would really work. And I think that students can do this too. So I'm going to show you my best contraption. It is 2 of these racks, and then you remove the pools and you put them into an overlapping pool. Hold on. I don't know. Do I need to just get further away from this maybe? Maybe.
Mm,
Can I see that? Hang on. You might be looking at a messy desk now, but you can see more of it. Yep.
Yeah.
Better?
Yeah.
Okay, so what's going on here? I would put the rows together and the columns together from the two separate matrices. Why do that? Because if I'm doing rows and columns, I'm going to have two positives, even though there's only one in my group of 36. When I have a group of 72, I hope there's only one in the 72. I want to separate it out. So I put the rows from group 1 and the rows from group 2 into this thing. And then I use it. I put my pools here and I put this sample into these two pools. And then I move these along and I put this sample into these two pools and I go all the way down. What does that do for me? I get 4 samples from this. I'm going to get 4 more when I do the other side, 8 samples. Can somebody tell me, these are Roman numerals. Give me some Roman numerals that are going to be positive pools. This is what goes in the PCR machine. Just call it out. 1, 2, 3, or 4, or some combination of that. I feel like you guys can't see this. Does anybody want to take a shot? Just take a guess.
Let's say 2.
2. Okay, if it's just 2, 2 comes up positive, no one else does, then I'm going to look. Maybe I have to go still further away. I don't know. I'm feeling like.
I can see the whole thing.
You can see the whole thing. Okay.
I think it's just the contrast isn't high enough to read.
Oh, I'm sorry. So this is number 2. And if you hopefully can see the holes,
Yeah.
that the only one that is only number 2 is this one. So I would know that the pool here is infected. And then I would go back to my matrix and that would tell me a row. All right, how about another combination? Instead of 2, what would it be? Give me one more.
3 and 4.
3 and 4. Okay, so I've got 3 and 4. And which one of these is 3 and 4? Well, 3 is in a lot of places, but those places, since these other ones don't light up, they don't count. So I would say 3 and 4. Why isn't it this one? This is 3. Well, it might be, right?
Yeah.
So I might have a question, but if my first sample was positive from this side, and I'm always doing my groups this way, then I might suspect this one as well. There's a problem with this thing if there's more than one positive, for sure, but it is my best scheme. You use 8 tests and you test 72 samples. So I'm still playing around with this. There is a robot that has a protocol designer that students could also design to and really get an understanding of what this pool testing is and how it works and doesn't work. I think it can make a really good exhibit. If you're interested, I have more slides on that. I see that it's,
There's a question in the chat.
yes, question. There's 99 names in the chat. Oh my gosh.
So are there some combinations that are missing? I see the first chunk is about pairs, and then you have a chunk of singletons, and you have a chunk of triples. Yes.
Yeah, so there are, I'm just trying to make unique signals so that each one is completely separate. And then later I found out about Steiner triples. And oh, I left my backpack. Steiner triples have the characteristic that no pairs repeat. So if you have 1, 2, 3, you'll never have 1 with 2, 2 with 3, or 1 with 3 again. And so that is a lot more resistant to this kind of overlapping that my idea suffers from. So yeah, there are others. There's tons of math to do around this. There's calculating the optimal pool size given your prevalence. You know, the Rwandans do something really interesting. They sort of pre-survey their samples, and they will go up to 80 in a pool. And what they do is they create a combination given their assumed prevalence that makes about a 37% chance that the pool will be positive. So if the prevalence is 4 out of 1,000, I think that's like 80 samples. If it was 1 out of 100, they would put 37 samples together and they would test those chunks. And then a certain percentage of the chunks would come up positive. Those chunks have a high chance of having a positive in them because they tested positive, but they also have a low chance of having more than 1 positive. And so that is what they use to then put into their contraption. The contraption they have is a cube. So it's like a parking garage, and you have the first level, second level, third level, you have the nearest row, the next row, the last row, and then you also have the space closest to the elevator, the one in the middle, and the far one. So in a 3 by 3 by 3, they've got 9 tests for 27 samples, and they should all have a unique place. So that is really interesting too. And then they move on to having more than 1 cube. So which cube are you in? I think the Steiner triples are really interesting. But my approach to this really comes from trying to just build it. And I am not as solid on the math. I have to really read up on it because combinatorics can get complicated. Pool testing was invented in the 40s by an economist named Robert Dorfman. He was looking for syphilis in inductees for the Army. So he was actually looking for people who were not infected. And syphilis is one of those diseases that doesn't show any symptoms. It goes through long latent periods. So there's tons of asymptomatic people running around. So that's where it started, and there's interest in it, and then it's hard to figure out. Yes, hypercube. I'm now looking at the chats. 1 over E, I'm not sure. And
So there's been some connections in the chat to error detecting or error correcting codes, and the 1 over E is a result from combinatorics about like that it's a bound on the efficiency of these kinds of things.
Yes, and understanding the error is a big deal. And that pre-survey thing that the Rwandan article, which if you want the link, you can get it, or let me reshare my screen and I'll show you where to find it. Do I get to share my presentation, by the way? Somehow?
Yes, we can upload that to our website.
Oh, okay. Well, that would be great. Where did it go? That's not it. Oh, sharing is paused. Resume share. Can I share anymore?
It might be computer issue. Mine does this during class sometimes.
Oh, or unspotlight. Oh, there we go. Okay. So right here is kind of a summary slide. You can see what the students did. We got, both of them went off. So we had number 2 as positive. And I made a little video because we didn't record it. But
This is just showing all white
uh-oh.
What a mouse.
with a cursor on it.
Oh no, why is that?
So maybe close the present and then go back to it.
Or just change the screen.
Stop share, reshare.
Yeah, there we go.
Okay, so this slide has a little video, speedy video. This is my pool testing presentation. Warning, it's 51 slides long. It has lots of links to these articles. I think that students could design a rack that does their scheme. There are lots of considerations. I have a little diagram of, people lined up at the lab. And if you do them one at a time versus you do groups, how many days does it take? What's the average time to return? But I think it's interesting, and it does work sort of over the web. And it's something that I'm 100% happy to share. I got straight B- in chemistry. It was from a major university, but still straight B-. So I'm struggling in the context a little bit to understand what the issues are in labs. Veterinary labs do this already. They'll have to test like 20,000 chickens. The thing that I was going to talk to you about was actually an error control thing as well. But the point is that there are lots and lots of ways to get our hands on math, and still ways to do it over the web, and ways to show kind of concrete manifestations, and ways to show what the questions are. Why do we need to do this error analysis? Well, because this isn't a perfect system. And what happens if there's more than one positive? Or do I get a clue that something's gone awry? That's another really good question, because you'd like to have some kind of signal that things are not lining up correctly, or that you have some overlap. I think the Steiner triples are really cool. So I am going to try to make that. You can definitely design a wooden rack that makes a cube, and you just have to, it will be even longer. But trying to figure these things out, trying to figure out what's being described, and working through that is a kind of a cool thing you can do. The rest of this presentation is more examples. If you want to go to Pioneer Farms and do math problems from the 1800s, they're just as horrible as problems today. Jim went squirrel hunting and killed 16 squirrels. If he goes at 4 days in a row, how many squirrels can he get? That kind of thing.
We need to wrap up.
Yes, of course. Any other questions or comments, or you're more than welcome to contact me. I hope this has been interesting. I hope that you'll join me in trying to get out there and talk about math outside of school as well as inside. I think it will help.
Excellent, thank you. And in our final 30 seconds, Meredith, do you want to give us a brief preview of what we're going to do next week?
Sure. So next week, I'm going to be talking about functional analysis. So my research is in complex functional analysis, and I know most of us don't do that. So I'm going to give us kind of a background on functional analysis, where we'll kind of view things through a linear algebra window, because secretly all I do is linear algebra. And then we're going to step up slowly through some thinking about various functional analysis concepts, and then I'll wrap up by talking about some of the orthogonal polynomials and optimal approximate stuff I've been doing lately. And you'll see that, again, it's just all linear algebra, but we throw like convergence in there so people get distressed. But you don't have to be, because it's not actually scary. It's fun.
Excellent. Please join me in thanking Lauren one more time for this session.
Thank you. Appreciate it.